This is a review of a four-bar linkage with Gruebler's equation. If you think back to a slider crank, one of the reasons why we like slider cranks is that it's only 1 degree of freedom, or mobility is 1. What that means is you need only one actuator to move the mechanism, right? It's, degree of freedom is the minimum number. So similarly with a 4-bar, we need only one. So I could drive it from the left, or I can drive it from right. I don't have that coupler tied down so you can see it spinning. If you're viewing this early in the class, we're going to spend a lot of time on slider cranks. If you're looking at this at the end of the semester, if you notice on the right side, the motion is limited between this side and that side. We'll see that in graphical methods where we can set what side, we can set the angle we want and figure out what mechanism satisfies it. So this is a crank rocker. It's a crank because the left side can go all the way around, where the right side can only rock back and forth. And we learned about this typically at roughly the end of the first week of the semester or into the second week. When we look at Grashopp's criteria, we can figure out the relationships between the lengths to give us a crank rocker, a triple rocker, a double crank, and so on and so forth. And later in the semester, we use a graphical method to say, okay, I know the general dimensions for crank rocker, but if I wanted to rock exactly from one point to another, what would that be? So let's take a look at the equation. So I'm going to do a quick screenshot of this and disconnect my keyboard here so that I can get my pin to work. And depending what order you're watching this in, the part of the LCD display is not functioning, and it'll be a couple weeks to get a new one. So we will make do when I hit some dead areas. So let's take a look here. So Gruebler's equation, as you probably recall, basically is F equals 3 n minus 1 minus 2 times J sub P, primary joints, minus J sub H, higher order joints. This is for a planar problem, and it doesn't handle special cases. An example of a special case would be something like this. If I have let's say I start with a 4-bar. And I add another link here. So we have the same motion with or without this second link. And the second link might serve a purpose since these bars are never infinitely rigid for support. But Gruebler's equation can't handle that. And you can do the math, but it's not going to quite do what you want. So let's continue with this one. So how many links? So what we said is the convention is at the ground, here's a ground, and here's a ground. We'll see this semester and in the future, that's traditionally called link 1, right? The ground is basically, think of it as connected as one piece. The other links, the order doesn't matter. I'm going to call this 2, I'll call this 3, and I will call this 4. If you remember from either the last video or from class, we letter the joints starting with A. Again, the order doesn't matter. I'm going to start here on the left. So this pin joint is capital A. This pin joint, which doesn't look like that because my links are not tied down properly, is B. My pin right here is C. My pin right there is D. So what do we have? So 4 links, 1, 2, 3, 4, so n equals 4. Primary links, remember, pins, and like we saw in the slider crank, a slider, or called the prismatic joint. So there's 4 pin joints here, primary. And higher order, we don't have any. Again, that would be a cam with a follower. Those would be gears. So plug it into our equation. 3, 4 minus 1, minus 2 times 4 minus 0 equals, no big surprise, 1 degree of freedom or mobility equals 1. And most importantly, what that means is we need only one actuator. So let me see if I can find the spot that will keep my computer from going crazy with all the other issues with the screen. But we always want to do a kinematic representation, which is a simplification. So if I simplify this, what would I have? I'd have a ground. I'd have a link. I have my third link. Oh, dead spot again. See if I can maybe make it a little shorter. Fourth link. Okay, so label them 1. I'll try it over here. 1, 1, 2, 3, and 4. And we would letter it as well to match. Pin A, B, C, and right in there is D. Stay away from the bottom of the screen. So that would be an example of using Gruebler's equation, again, for simple planar problem, to just show that as 1 degree of freedom. So let's take a look at some other cases. So let me close that up. Let me see if I can get a blank sheet. This is another one of those areas on my screen that doesn't work. All right. So as I plug in my keyboard, so I can pull this up. Let's take a look at a case that might remind you of status. Here we go. Got a blank sketchpad, and that beeping is me putting the keyboard in and out. So we've looked at a case with 1 degree of freedom. What if my mechanism looks like this? So these are all pin joints. So do you recognize what this is? Well, think about this, right? These grounds are always considered connected. You've got a triangle there. Yes, they're all pinned, but like in a truss, this is not going to go anywhere. So how many degrees of freedom? I would expect 0. So let's do the kinematic representation, or the kinematic diagram. So what do we have? Ground, typically a straight line, ground. Let's number them. 1 is always ground. The other ones don't matter. I'm going to call it 2 and 3. So 1, 2, and 3. Let's put our letters here. This joint right here is pinned, A, pinned here, B, pinned here, C. So we've got A, B, and C. So what do we have? N, number of links is 3. Primary joints, you have them to all be pinned, 3, our A, B, and C. Higher order, right? Cam followers, gears, we don't have any. Plug it in. So F equals 3, 3 minus 1, minus 2 times 3, minus 0, equals 0. So this is what we call a lock mechanism, right? It's a structure. All right, let's take a look at one. With a little more mobility. What if my mechanism looks like this? So it looks a little bit like a 4-bar. It looks a little bit like a slider crank, right? But it's neither, right? It's a 4-bar that slides at the right end, or it's a slider crank with an extra link. So let's see if we can get a handle on this. So let's go through the same process. Okay, ground is always 1, right? Label my links any way I want, 2, 3, 4, and the slider is 5. Let's do our joints. The pin joint in here is A, B, C, D, and E is the one that slides, otherwise known as a prismatic joint. Let's do the kinematic representation now. Simplification of the shape. Okay, I drew a little lower 3 because it doesn't make a difference what position it's in. So what do we have? 1 again, and now these have to be 2, 3, 4, and 5 because I've already assigned them. So typically for homework, you'll take your photograph, whatever it is, the drawing, you'll label right on top of it, and then you create your kinematic representation. So we got A, B, C, D, and E, which slides or is prismatic. So how many degrees of freedom do you think we have? If I only controlled it from here, let's say, with 1, I can think of different combinations where this can end up. So for instance, if the slider doesn't move, maybe it ends up in this position. Or if the slider does move, I could have a case where even if I crank it to here, different color here, even if I crank it to here, what else could I get? The slider might slide back to there, and then I can come up with some combination that hits that, maybe up, maybe it's down. So what do we have? So we said there's 5 links, 1 through 5. Primary joints, how many are pinned? 1, 2, 3, 4. I have 4 pinned, plus 1 prismatic, or slides. So it's equal to 5. Higher order, right? Gears, can't follow her, don't have any. So let's plug it into our equation. Gruebler's equation, again, just for planar cases. So we have 5 minus 1 minus 2 minus 5 equals 0. 12 minus 10 equals 2. Oh, so it's the bottom of the screen already. Let's see, how about here? I'm trying to get a spot that still works. Equals 2. So that means I need 2 actuators. What are my 2 actuators? Maybe it is a motor at this first crank. So let's grab a brown. So over here we went before, maybe there's a motor. Maybe there's a second motor. Or maybe I have something to drive the piston. Sorry, that is not, screen's not responding that well there. So there's a case we looked at 1 degree of freedom. We looked at a lock mechanism, which was 0. And we looked at a case of 2 actuators. I could have a negative value if I have an extra support in there. I could go negative. One thing you want to One thing you want to look at, though, if I have an area where, let's just say at a particular spot, multiple links meet. So I'm not sure what's happening at the rest of these, at A, B, C. But at D, what's happening? Let me try to make it a little bit easier. C, D. So what do I count that as? So at D, I would say, even though, yes, I can make it with one pin, one bolt going through, mathematically, I look at it as let's say, link 2, 3, and 4, that 2 is pinned to 3, 3 is pinned to 4, or some combination. So I would treat that as 2 pins in terms of my equation. And the rest of the drawing, it just depends what I actually have. If I have a mechanism where I don't know what is clearly the ground, such as a scissor, then I can just pick whichever one I want, whichever link makes the most sense to me, and give that a designation as 1. So this is, again, another quick review of using Gruebler's equation for a simple planar problem, but watch out for combined mechanisms. So an example where it's not going to work is if, let's say, I make a slider crank, right? That's the degree of freedom, that's 1. What if I come off the other side and make a 4-bar? So I think we can agree that would physically work. That would be 1 degree of freedom if I do what? I would have to connect this link and that link into 1. So let's see if I can do that with this software. Let's see. Yep. That seems to work. So let me go and make another link here. I'm going to pick a different color. So now I have what's called a tertiary link. These other ones were binary links where there's 2 pins, and here's a tertiary link. So as the link, let's say, rocks back and forth, I could be driving the slider crank on the right, the 4-bar on the left. But the Gruebler equation probably will not give me the right answer. So hopefully this review was helpful.